Hello and welcome to the 23rd lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. So we were discussing about controllability and observability. We have proven necessary and sufficient conditions for controllability and observability, and now we were trying to relate controllability with control. So for that I had defined what we mean by behavioral controllability. So this is my box of laws that are satisfied by the variables, the manifest variables of the behavior, right. A controller would mean that to these all of these variables or to a smaller number of variables, doesn't really matter here. You add additional laws which you call the control, and the system must be such that it satisfies both these laws. Yeah, it satisfies the laws coming from the behavior or the plant, it satisfies the laws coming from the controller. Okay. Equation wise, if suppose we have done this input output partitioning and have written the equations in this form, the new laws are, what should we call them, let us say n xi and d xi, right. Perhaps I can put a minus sign over there. It's really of no significance. Together this is what we have, yu equal to 0. This is the controlled behavior. This is the controlled behavior, right, given by this equations, yu such that these equations are satisfied. Now if that is the situation, what we mean by pole placement? Well, to make it autonomous we should have this guy to be a square matrix such that, now if you remember when we derived, when we talked about autonomous systems, if you remember, we needed to find out the determinant of, so autonomous system, say kernel of R xi, R is a square matrix, we need to find out the determinant of this guy, right. Those are the roots of this guy, the roots of this polynomial are the ones that determine the response of the system, isn't it? If you remember, what did we do? We looked at this R xi and then we did some unimodular row operations so that it became upper triangular, right. The moment it becomes upper triangular, and because all the operations are unimodular operations, then the determinant of R is the same as the product of this diagonal entries. Yeah. Why are they important? Because look at this guy, the standalone equation, the last equation. The last equation is, suppose this entry was some d g xi, right, acting on wg is equal to 0. What are the solutions of this guy? The solutions are given by the roots, isn't it, e to the power lambda t, where lambda is the root of this d g xi. And likewise when we do this back substitution, each time the ith variable satisfies the equation di is equal to some linear combination or some polynomial differential operator acting on the other variables, something that acts on wi minus 1 up to wg, right. That's how you get the solution. So once again the mode of the solution is determined by the roots of this polynomial. So together, in fact, when you look at the product, all the roots of these products, all the roots of these these diagonal polynomials, they are the ones that dictate, that describe the solution, isn't it, right. There is another easier way of understanding why this is happening, because essentially what we are trying to do is, like before, look at this R xi w equal to 0. To get solutions w, all I need to do is I need to find out lambda complex number such that R lambda loses rank, right. and where does R lambda rules rank, for which complex number lambda does R lambda have lesser rank than its size. Yeah, those are precisely the roots of the determinant of R xi. Okay. Now, if that is so, then find out such a root, find out such a root, find out such a root, find out R lambda, find out a non-zero vector which is guaranteed to exist, because this is not full rank. Yeah, it is a square matrix, not having determinant equal to 0 means that there are non-zero vectors in its kernel. So, find one such vector, and then V e to the power lambda t is a solution in the kernel of R xi, like we have done before, as simple as that. Although I am skipping the nitty gritties of this, because there could be multiplicities and there could be solutions like V t to the power lambda t and stuff, but we are sort of not interested in that here, because as far as the way the solutions are going to die down, that trend is concerned, that trend is governed by the roots of this determinant. So, pole placement here would mean to place the roots of the determinant of this guy. So, the question is, can we place these determinants arbitrarily? Can we? So, here the question is even broader, let's. So, given a polynomial f xi, is it possible to find n xi d xi polynomial matrices of proper sizes such that, notice, p xi minus q xi, I did put a minus, that does not really matter, d xi, determinant of this is exactly equal to f xi. Is it possible? Is it possible to find out a controller so that the control system has its characteristic polynomial, let us say characteristics polynomial, that is the determinant of this square matrix, the characteristic polynomial of this system, the characteristic polynomial of the controlled behavior matches exactly with the given polynomial. Is it possible? The answer is that this is possible if and only if, this is possible if and only if this matrix R xi, or the behavior, if and only if kernel R xi is controllable, behavioral controllability. Okay. Suppose it is not controllable, we prove it this way. Suppose not controllable, right. So, let me just do it a little formally, so that we do not get to, yeah. So, restating this statement, restating this, what we are saying is pole placement possible if and only if controllable. What we are showing now is this direction, pole placement implies controllability. Pole placement, it is possible to do arbitrary pole placement, implies controllability. This direction is what we are going to prove, but we are proving it the contrapositive way. We are saying that suppose it is not controllable, then we will show that this also means that it is not possible to do pole placement. Why is that so? Let us see carefully. Yeah. So, not controllable means R xi, assuming full row rank, that is without loss of generality, assuming full row rank, R xi is not factor left prime, okay, which then further means that there exists lambda complex number such that rank of R lambda is strictly less than the number of rows, that is G. Okay. Now, so look at R xi. When we put a controller, we put extra laws R c xi. together, this is now Q cross Q size matrix, so square matrix. Okay. Now notice the fact, if it is a square matrix, no matter what RC xi we choose, if I evaluate this matrix at xi equal to lambda, I will have R lambda over here and RC lambda over here. Can this be full row rank? Can this square matrix be full rank? Of course not, because the top rows are dependent. R lambda loses its rank. The top rows already are dependent. Yeah, how many rows are there? G. This supplies Q minus G some extra rows. But even if these guys are all linearly independent, yeah, and they are linearly independent with these guys as well, it doesn't really save us from losing the rank, because the first few rows already are losing ranks. Correct? If the first few rows are losing ranks, then I can always, in other words, I can always find a constant vector here and then pad it with zeros, so that this guy is equal to 0, which means there is something in the left kernel. So obviously this cannot be full rank. And see, I was able to do this for every lambda for which this is true. That means for all those lambdas for which the rank was falling for this guy will immediately show up here no matter what controller I put. Alright. One might ask, why restrict your controllers to only these many, why you do not have more controllers? That comes from the restriction of input and output, because you see the controller, so what is the input cardinality and output cardinality of this guy? Because I have assumed full row rank, number of outputs is G, so the number of inputs is Q minus G. So from your standard control theory point of view, if this is U, this is Y, the number of Y's that are there is G, the number of U's that are there is Q minus G. When you put a controller, the controller should have signal flow in the opposite direction, right? So the number of outputs is the number of inputs for the controller. So that means the number of outputs for the controller must be equal to the number of inputs of the plant. So the rank of this controller must be equal to the number of inputs, which means this is Q minus G rank. So in order to have a Q minus G rank controller, and if we assume full row rank, which is without loss of generality, then the size of RC lambda must be Q minus G cross Q, right? That is how you make sure that this is square and square and full row rank. Okay. So even if you assume square and full row rank over the ring of polynomials, if there are lambdas for which the top part, that is the plant, loses its rank, you can never save the control systems from losing its rank, which means these lambdas will always be there in the roots of the determinant of R xi, RC xi, okay, which already means that arbitrary pole placement is not possible, because these factors S minus lambda 1, S minus lambda 2 dot 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 up to S minus lambda R, and perhaps their powers also, where these lambda i's are in this set. Yeah. So look at all those lambdas for which the plant loses its rank. Those lambdas will always show up in the roots of the determinant of the control system, which means that the determinant of the control system must have this factor. If it has to have this factor no matter what, how can this be arbitrary pole placement? Because you see, this was an arbitrary polynomial given to us, f, somebody gave us. Why on earth should this f contain these things? It need not, right? So therefore arbitrary pole placement is not possible. So not controllability implies pole placement is not possible. Now to prove the other way around is a little more difficult. This is kind of trivial. The other direction is what we need to show. Controllability implies that arbitrary pole placement is possible. So we start with R xi, yeah, and we assume that it is factor left prime because it is controllable. because it's arbitrary, because it's factor left prime. Once again I need to add this RC xi below, so that this matrix, this determinant is equal to the given f psi. How do I do this? You see, how do I do this? Well, to do this, once again, don't take this as an algorithm. This is an existential proof, yeah, which will show you that okay, such a thing that is possible. Whether to use that as the method, that is questionable. But let us at least get a theoretical proof of why should this be possible to place to find this RC xi, so that the determinant of this is exactly equal to the given polynomial. So because R xi is factor left prime, its Smith form will look like this, right? We have seen that factor left prime implies the Smith form is of this form. Now to get RC xi, notice this guy. So I will just now concentrate on this Smith form and I will do something about this. I will look at this U xi, I will look at this I g 0, and I will extend this matrix to have 0 I q minus g. So then this will be a q by q matrix, square q by q matrix, yeah. Multiplying V xi is okay. Multiplying U xi of course is not possible, so I add these guys, this q minus g number of size identity, and pad it like this. Yeah, so I should write a little bigger these guys. Get rid of this. Yeah, I write this as I q minus g. That's the size. I hope it's okay. This was a G by G matrix. This is a Q by G matrix, Q minus G times Q minus G matrix. So overall, this is a Q by Q matrix. This is Q by Q. This is Q by Q. This is Q by Q. So it's a square matrix. This is not R xi anymore. Let me get rid of this part. I have just done this extra bit of trickery on this guy. Now, tell you what is this matrix? What can we say about this matrix? This matrix has a unimodular matrix on the right. This is actually identity of size q. This is in fact identity of size q. So this is obviously unimodular. This matrix is a block diagonal matrix where this block is unimodular and this block is identity. So overall this also is a unimodular matrix. So in fact I have a product of 3 unimodular matrices. So this is a unimodular matrix. Okay, right. So now what have we done? R xi is equal to U psi IQ 0 V xi, right? Okay. To this I do the following. So if I now just look at this guy, yeah, just look at this guy, look at 0 I q minus g multiplied by V xi, yeah. So if I now take R xi and put below this thing 0 I q minus g acting on V xi, then this entire thing is nothing but U xi 0 0 identity of q minus g multiplying I q 0 0 I q minus g multiplying V xi, yeah, and this is a unimodular matrix. So that means this is a unimodular matrix. Great, no? Because it is a unimodular matrix, what I have done essentially is that given an R xi, I have shown R xi factor left prime. I have shown that this implies there exists, let us say, an RC 0 xi of size r q minus g times q xi, such a matrix such that when I put them as a controller, I get this matrix as a unimodular matrix. What is the determinant of a unimodular matrix? It is a non-zero constant. Okay? Now here comes the trick. See, my goal was to place the poles arbitrarily, so that the determinant of this guy was the given polynomial. Yeah. But now instead what I have obtained is, I have obtained a situation where the determinant is a constant, determinant is a non-zero constant. Determinant of r xi is r0 xi is equal to a constant k, which is a non-zero real number. That is not enough, right? I need it to be f xi. Now rc xi, define it to be like this. Notice carefully, rc0 xi, take this, yeah, take rc0 xi, look at its rows. This is rc0 xi, look at its rows, look at the final row and multiply the final row by f xi divided by k. K is a non-zero constant, so it is fine. So this entry was alpha 1, then let me write it properly, this is not visible. This much is okay. Yeah, suppose the last entry of rc xi was say a1. I am getting rid of the xi's. Yeah, let me write it, a1 xi, a2 xi, dot 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 up to a, what was the size, q, aq xi, right. These are the last entries of the last row. Multiply each of them by f xi divided by k, f xi divided by k, f xi divided by k. What does this do? If this is your rc xi obtained from rc0 xi, then notice if I have r xi and rc xi, what will be its determinant? It is exactly the same matrix. So let me write down, this matrix is the same as r xi rc0 xi, yeah, but the last row is multiplied by f xi by k. That means this matrix is the same as this diagonal matrix, which is almost like an identity, but the last entry is changed by f xi divided by k. That is what multiplies the last row of this entire matrix by this guy. Yeah, so it is just a multiplication from the left by just a row operation, multiplication from the left by this matrix. So then what is the determinant of this guy? The determinant must be determinant of this into determinant of this. What is the determinant of this guy? F xi by k. What is the determinant of this guy? K. K cancels out, I have f xi, right. So I have my controller. Yeah, so what have we essentially done here is nothing fancy. It is just this fact that given a factor left prime matrix, it can be completed to a unimodular matrix. That is the crux of the matter. Every factor left prime matrix can be completed to a unimodular matrix, and once you have, by adding extra rows, once you complete to a unimodular matrix, then getting an arbitrary polynomial is very simple. Is just change the last row of the controller by multiplying to every entry this polynomial that you wanted divided by the constant of the unimodular matrix is constant, that is the determinant of the unimodular matrix. That is it. So, you have done arbitrary pole placement. So, we have essentially proven this implication as well. So, by that we have also proven this statement that controllability if and only pole placement, arbitrary pole placement is possible if and only if controllability. What interesting fact that comes out of this analysis also is the fact that if it is not controllable, look at this R psi, if it is not FLP, if it is not controllable, is not factorial F prime, then these roots, these complex numbers for which this guy loses its rank, these are in a way roots that are unchangeable by this kind of control. So, these controls will never be able to shift these modes, they will continue to be there in the control system no matter what controller you put. So, these adamant modes are then understandably called uncontrollable modes. Okay. And then just like your multivariable control, some systems which may not be controllable, but have their uncontrollable modes, lambda uncontrollable, which is by definition this set. If this is in the open left half of the complex plane, then at least these uncontrollable guys will die down as t tends to infinity. When you put this controller, these modes you will not be able to change. So, each of these guys will give you trajectories like e to the power lambda t, which dies down like e to the power lambda t, but they will go to 0 as t tends to infinity, right. So, no wonder in such a scenario the system is called stabilizable. Right. Likewise, you have the analog of the idea of detectability also, unobservable modes, detectability and so on, but that will go to you as an exercise. I will give a detailed exercise problem which will deal with topics like this. Okay. So, I guess we can end today's discussion on this note. From the next lecture onwards, we will learn, we will be into the thick of things as far as data driven control is concerned. We will start with this idea of how to identify a system behaviorally when you have information about one of its trajectories or multiple of its trajectories. We will talk about this idea of most powerful unfalsified model. So, MPEUM, that will be the starting of our discussions on data driven control. This and many more is what we are going to see in the next few lectures. Till then, take care of yourselves. Bye.